there's a lot of structure in this picture that we've got, and we can understand the relative positions of the elements if we think about the electron configurations that we've been looking at when we've been talking about individual atoms. So I'm going to clear away some of this clutter, and I want to focus on these three elements over here: oxygen, fluorine, and neon. So an oxygen atom has a nuclear charge of 8 plus. There are 2 core electrons in a 1s2 configuration. That's the helium-like configuration. So those 2 core electrons are tightly held close to the nucleus, and beyond those core electrons, the valence electrons are attracted by the 8 plus in the nucleus. They're repelled by the 2 minus in the core. So the net attraction that the valence electrons feel, the effective nuclear charge, is 6 plus, and that charge is felt by the 6 valence electrons in oxygen. So those valence electrons are feeling an effective attraction of 6 plus toward the nucleus. That holds them pretty tightly, which is why oxygen has a fairly high ionization energy. And furthermore, when a new electron joins the oxygen atom, it's able to experience that high effective nuclear charge, and so a fair amount of energy is released when an electron is added to an oxygen atom. Now, this new electron that comes in, there is a trade-off. It's attracted by the effective 6 plus toward the nucleus. It's also being repelled by the 6 valence electrons that it has to share the atom with. But the valence electrons are spread out over a large region of space, and so the attraction that this new electron is feeling for the nucleus outweighs the repulsion that it feels for the other valence electrons. And so on balance, this new electron is in a good place, and a lot of energy is released when that electron joins the oxygen atom. Now, fluorine is over here in our graph. A fluorine atom has a nuclear charge of 9 plus. It also has a core of 2 electrons. So beyond the core, the effective nuclear charge felt by the valence shell is 7 plus. There are 7 valence electrons, 2s2, 2p5, and those electrons are attracted by an effective force of 7 plus toward the nucleus. That's more than the 6 plus felt by the valence electrons of oxygen. And so the electrons in fluorine are held even more tightly than they are in oxygen. Fluorine has a higher ionization energy. And also, when a new electron comes in to join the party on fluorine, that 7 plus effective nuclear charge means that even more energy is going to be released when that electron joins the fluorine atom. So fluorine has a much higher electron affinity than oxygen does. Now, moving further to the right on the periodic table, neon is way down here on our graph. Neon has a nuclear charge of 10 plus. There's still 2 electrons in the core, so beyond the core there's an effective nuclear charge of 8 plus, which is felt by the 8 valence electrons on neon. And so those valence electrons are experiencing an attraction of 8 plus. That means that they're held very tightly. Neon has an even higher ionization energy than fluorine or oxygen. However, if we were to bring in a new electron onto fluorine, it's not going to want to join the atom. Fluorine has a very low electron affinity. In fact, its electron affinity is negative. And the reason for this is that there's no room in the valence shell for an additional electron. And if a new electron wanted to join the neon atom, the only place that it could come in is in the 3rd energy level. in the 3s orbital. And if you think about it, if an electron were to do this, if it were to hop into the 3s orbital on neon, it'll be attracted by the full 10 plus of the nucleus, but it'll be repelled by all 10 of the electrons that were originally on neon. And so the that new electron is not going to feel any net attractive force for the nucleus. And worse than that, if a new electron were to come into the atom, it's going to repel all of the electrons that were already there, raising their energies. And so that's why the electron affinity of an atom like neon is negative. It has no tendency to pull in an electron, and in fact, you would have to push an electron to force it to join a neon atom. So neon has a negative electron affinity. So the effective nuclear charge that would be felt by that new electron would be essentially zero. So this actually illustrates a really important point, which is atoms like neon that have a filled valence sublevel, so filled s and p sublevels, tend to be very stable. The valence electrons are held very tightly, so such atoms don't want to lose electrons, and also these atoms don't want to take on new electrons. So atoms like neon and the other noble gases, they're very stable. They tend to keep to themselves. They don't interact with other atoms. Now, another interesting thing comes in if we look to the left of oxygen and look at nitrogen on this graph. So nitrogen is down here in our picture. It has a much lower electron affinity than oxygen, and let's see if we can understand why that is. So nitrogen has an atomic number of 7. The nuclear charge is 7 plus. There are 2 core electrons, and so beyond the core, the effective nuclear charge felt by the valence shell is 5 plus. There are 5 valence electrons, and those valence electrons are they're being attracted by less of an effective nuclear charge than in the case of oxygen. It's only a 5 plus that they're feeling versus 6 plus in oxygen. But on the other hand, the last electron in oxygen is forced to pair up in one of the 2p orbitals, and it doesn't really like that. And so as a result of that additional repulsion, the ionization energy of oxygen is actually a little bit less than nitrogen. In nitrogen, all of the p electrons each have a separate orbital to themselves, so they don't feel that extra repulsion. So nitrogen has a slightly higher ionization energy than oxygen. But on the other hand, if we imagine adding an electron to nitrogen, that new electron has to pair up in one of those p orbitals. That introduces extra repulsion, and the lower effective nuclear charge just isn't enough to pay for the additional repulsions that show up in nitrogen. And so that's why nitrogen has a much lower electron affinity. And in fact, the electron affinity of a nitrogen atom is slightly negative. And this illustrates another interesting pattern that shows up in a number of atoms in the periodic table. And this is atoms whose electron configurations have half-filled sublevels, like nitrogen has the 2p3, has a half-filled p sublevel. Such atoms tend to be stable. They're certainly not as stable as noble gases. It's not as stable as having filled s and p sublevels, but nevertheless, it is a fairly stable situation. And this helps explain, in part, the distribution of nitrogen and oxygen on Earth. So oxygen has a much higher electron affinity. It has a much greater tendency to form ions than nitrogen does. And so oxygen most of the oxygen on Earth is actually bound up in ionic compounds in the Earth's crust. So about 91% of the oxygen atoms on Earth are bound up in rocks. By contrast, nitrogen has a much lower tendency to form ionic compounds, and a much smaller fraction of nitrogen is bound up in rocks. Only about 13% of the nitrogen atoms on Earth are bound up in the Earth's crust. And there are a number of reasons for this, but one of the things contributing to this is the extra stability that nitrogen has because of its half-filled p sublevel. And so these patterns that we've been seeing with filled and half-filled sublevels, they actually help us to understand those funny metals that are in the lower left corner of our graph here. So in that corner, two of the metals, magnesium and beryllium, are up here. They have filled s sublevels in their valence shell, and having those filled sublevels means that they are reluctant to take on new electrons. That's why they have negative electron affinities. Over here, mercury, cadmium, and zinc, they're all over here. They have a filled d sublevel, so they also are fairly reluctant to take on new electrons. Manganese is over here in the middle of the transition metals. It has a half-filled d sublevel, and so that explains its low electron affinity. The last one, plutonium, is in a similar situation to manganese. It's a little bit harder to explain that, but it's in a much similar situation to manganese, and it's experiencing the half-filled sublevel stability. So that concludes our overview of the atoms in the periodic table and their tendencies with regard to electron affinity and ionization energy. And in the next video, we're going to take a look at how this bears out on the bonding picture of these atoms.